Morning, everyone. So yesterday we started looking at what I refer to as ice tables, basically introducing a little bit of the math and the numbers for equilibrium. We saw if there was a sense of time passing, I would use this ice table here to record down the information I know initially. We knew that the change line is sort of shifting, approaching towards equilibrium, and then by the time we get to equilibrium, we can plug it basically into our Keq expression and solve for any unknowns. So I was thinking of just practicing through a question or two from there, and then afterwards we're going to take a quick look at something called the trial Keq just to finish off this chapter. So to begin with here, we'll do this for a warm-up. For all these ice table style questions here, we're always going to be referring to an equation. So I'm going to take the Haber process again. We have N2 and 3H2. These are all gases. They're currently in equilibrium with 2 ammonia as a gas. I'm going to give you the setup of the problem here. So it's a word problem. So let's take 4 moles of N2 and 5 moles of H2 are placed into a 2-liter bulb. The word bulb here just means it's a container. So basically, I know the space in the container here is 2 liters, and what I decided to do initially is I pump in 4 moles of my nitrogen, and I pump in 5 moles of my hydrogen. Right? They didn't need to say, oh, by the way, I didn't pump in any ammonia, right? That's sort of implied here. Now, what it informs me here is after reaching equilibrium, so there's that sense of time passing. It could be in the matter of seconds that it reaches equilibrium. It could take minutes, even days to get there. But upon reaching equilibrium, we find there are 0.80 moles of ammonia present. Right, so I'm given some information about upon reaching equilibrium. For the starters here, they're just going to ask you here, calculate the Keq. Find for me the value. I didn't specify what temperature I'm at, but at this temperature here, given these relative amounts here, can you find for me what the equilibrium value is? There is a sense of time passing because there's a certain initial. I put this into the bulb here, then it reaches equilibrium. So I know I'm going to use ice tables. For ice tables, it's most convenient to actually use concentration. So I'm actually going to calculate these concentrations first. And I'm going to put an I for initial here. I pumped in 4 moles worth of gas, but because we were in a 2-liter container, our concentration is only 2 molar. Similarly here, I pumped in hydrogen initially here, a little bit more hydrogen, so 5 moles divided by 2 liters, this gives you 2.5 molar. I'm also given one of the numbers at equilibrium, so the ammonia, this is at equilibrium, so you can put E or EQ here. Also gives it to me in moles, so I'm just going to convert it. Moles divided by liters always gives me concentration 0.40 molar. As we set up our ice table, we're actually going to use the equation as our heading. So let's take N2, 3H2. This is in equilibrium with 2NH3. We're going to do our ice table ICE down the side. The I, again, stands for our initial. Initially, you pumped in, yes, I knew the actual moles, but because our volume is actually 2 liters, I'm actually going to use concentration. So you can make a note to yourself, use concentrations on the ice table. Technically, it would work with moles as well, but we'll see in a second. Because Keq later on wants concentration anyways, it's nicer if they're already expressed in molar. Anytime you need to convert to moles, you just multiply out the volume. So initially, you pump in 2 moles worth of nitrogen, 2.5 moles worth of hydrogen, and again, because I didn't imply to you actually put in any ammonia, you can actually assume that we actually use 0 ammonia. We know one of these equilibrium values, so it helps us from needing to do an X here. The ammonia concentration, so down the column of ammonia, it says we create 0.40. Those are the starting numbers as given to you. Couple observations already. Notice that, yes, I know the mole ratio here is for every 1 part N2, it reacts with 3 part H2, but since the container is in front of me, I can pump in whatever amounts of N2 and H2 I want. So you see that the initial row doesn't necessarily need to follow the mole ratio. I decided to pump in 2.5 and 2N, right? I could have pumped in more of the N2 if I want, right? So the initial doesn't necessarily follow the 1:3 ratio. The line that has to follow the mole ratio is during the reaction. So this change line, the change must follow the mole ratio. Because the change line here involves using the reaction itself, for every 1 N2 that reacts, it always does react 3 times the H2. So in terms of the drop, the drop in H2 will always be 3 times as much as what the N2 is. Right? So that's one observation. The other observation here, very similarly here, we actually calculated it. It's almost like we took a meter at the end, we reached equilibrium, and we said, oh, the amount of ammonia at the end is actually 0.40 molar ammonia. I'm telling you, that's the amount of ammonia that we have. You don't suddenly come along, well, what about this 2 here? Doesn't that suddenly become 0.8? No, they've actually measured for you. This is the exact amount of ammonia. Just like the initial line didn't care about the mole ratio, this line here will also not care about the mole ratio. So the only line that refers to the mole ratio is the change line. We need to decide which side goes up, which side goes down. For these starting problems here, it's a little bit easier because one side is 0. I can't drop any lower than having no NH3. As I approach equilibrium, you can refer to it as shifting towards equilibrium. You can just say, oh, the reaction proceeds towards equilibrium. I know I have to gain on the NH3 side. Once the product side in this case here is positive, the other side has to be minus. Again, following the mole ratio, if I am going to create ammonia, I would need to shift right. I would need to form some of the reactants into products. I would actually lose my reactants. Normally, if I'm not given an equilibrium row, I'll practice another one of these with you, you would use an X. In this case here, because I actually know one of the numbers, doesn't matter which one, I can actually figure out the change. I started off with no ammonia. I gain 0.40. That's what allows me to hit 0.40 at the end. And we see that this change line, which goes according to the mole ratio, well, if this one here gained by 2 parts, I would lose half the part nitrogen. So I would lose 0.20 as nitrogen. This one here is in a 1 to 3 ratio. I would lose 0.60. The only line that follows the mole ratio is the change line. Anytime you have the I and the C line, you basically crunch through the math. 2 minus 0.2 is basically 1.8 here. 2.5 minus 0.6 is 1.9. So I am at a certain temperature where at equilibrium, because I know how much ammonia there is, and because the change line follows the mole ratio, I actually know what the equilibrium amounts of N2 and H2 are. Took a little bit of work, but once you have this row here, you can sub it directly into the Keq expression. Even when you're ready to actually punch in the exact numbers, these are already concentrations, that's awesome. I would still write out the Keq expression. Remember, Keq in general is this whole notion. It's a measure of how many products I have divided by how many reactants. The products this time I have is just ammonia. The numbers go up into the powers, so ammonia squared divided by N2 divided by H2. Every now and then they try to sneak in, oh, there's a 3H2. Shouldn't that be 3H2 like that? I've already dealt with the mole ratio in this point here. In general, there shouldn't be numbers in that square bracket there. And we saw more in yesterday's lesson. Basically, the balance coefficients go up to become the powers. Once you have these values here at equilibrium, you just punch them in. So 0.40 is for the ammonia, 1.8 is for the N2, and the 1.9 cubed is for the hydrogen. This is just going to give you some value, and this is called the equilibrium constant at this temperature. Let's figure out what this is here. Punch it all the way through. I get the equilibrium constant being 0.013, right? So that's a constant. Keq here, it's best to say no units, right? It's just this ratio between how many products and how many reactants that I have. And what we conclude here is because the K is so much smaller than 1, essentially it means reactants are favored. It means even though we are hitting equilibrium, we're hitting this sort of balance, we're at a certain temperature that we have way more reactants. Looking at the numbers, that's true. We have like 1.8, 1.9 of my reactants, but only 0.4 of my products. And that's what this equilibrium constant actually expresses for you. Using the same equation, let's just practice through another one here. I think I borrowed this from one of your textbook problems here. Slightly different arrangement in terms of what information they give you, but we'll see if we can work our way through. This time we're going to be at a different temperature. Let's say the Keq here is given to me as Keq is 3.0, right? So I know the Keq is different, so I know I'm at a different temperature. Only temperature can change Keq. Let me just read you the wording of this problem here. Enough NH3 was added to a 5-liter container, or you can call it a 5-liter bulb, such that at equilibrium there is 2.5 moles of N2. Right, I just give you that one number, right? Tell you something about the N2. The question here is how many moles of NH3 were initially placed. So let's just draw a picture if we can here, and I encourage you to just pause the video. You can try it out for yourself. The picture is actually quite simple. We start off, this time our bulb is 5 liters worth, right? So if I ever want to do concentration, I just basically divide out the 5. What I do is I pump in some unknown amount of NH3. So I'm going to pump in some question mark. In fact, at the end of the day, I want to know how many moles of NH3 did I pump in initially. That's the only chemical I pumped in, so I can imagine the N2 and the hydrogen at initial, it's actually 0. At the end, they again give you one of these values here. Unfortunately, again, that's just in moles. Let's just calculate that first. So what is the concentration of N2 at equilibrium? I calculated, I went in with a meter, I measured 2.5 moles. It was a 5-liter container. I have enough N2 to make my solution 0.50 molar as a concentration. We're going to use our equation as our heading. So N2 and 3H2 are in equilibrium with 2NH3. We'll do our ICE down the side here. This equilibrium value for N2, I look down the column for N2 at equilibrium. We know it's 0.50. This time we have an unknown amount. This time what we're after is the initial line for NH3. I want to know how much NH3 I actually subbed in. And again, what's implied here is because I just pumped in NH3, I can assume that I actually had no N2 and no hydrogen at the beginning. So basically, I'm just going to work through my values. Anytime you're given one of these equilibrium lines, you don't need to deal with X. We'll deal with that in the next problem here. Well, I start with 0. I can't drop any lower than 0, so I know this side has to be plus. How much do I gain by? I gain by 0.5. The change line has to follow the mole ratio, so it's a 1 to 3 ratio. This one also gains, but this gains by 1.5. This one here drops by 1.0. Right? Anytime you get the I and the 0, you just do the math. 0 plus 1.5, well, that's 1.5. I have no clue what this NH3 is. You could call it X, just to make it a little bit different from usually we do X for the change line. I'm just going to call it Y. It's just any variable. It's just some unknown that I punched in here. That's the concentration. Even though I don't know what the placeholder is, I just crunch through the math. What's Y minus 1? Well, it's Y minus 1. Right? And in general, anytime you have this equilibrium row, you're ready to sub into the Keq expression. As I mentioned before, even though we already have a lot of the numbers, I would still write out the Keq expression. Keq, in this case here, we just did this. Ammonia squared divided by N2 divided by H2 cubed. The numbers become the powers. We are at a certain temperature where the Keq is actually 3, so I know products are actually favored. Let's punch in our numbers. We have 3. We have a y minus 1.0 squared divided by 0.50 divided by 1.5 cubed. It is also one equation, one unknown. It's just a slightly different way of styling the problem. Let's just go 3 times the 0.5 up times the 1.5 cube up, and therefore I'm getting here 5.0625 is equal to this y minus 1.0 squared. Usually this would have ended up as a quadratic, right? I have a y squared term. Walk you through one of those later on. But remember in Chem 12, we don't need to deal with quadratic. They'll usually set up the number so you can just do an easy square root. So let's just take a square root of both sides here. The root of this 5.0625 is just 2.25. That's going to get rid of the square for me, and therefore the y is equal to 3.25. Right? Now, it was a little bit of algebra work here to actually get to this y here. Do yourself a favor and go back and reread the question. What were they actually after? They wanted you to calculate the initial amount of NH3 in moles. So we look at our ICE table again. The initial amount for NH3, oh, that was the y. Perfect. So they wanted you to find y. Only problem is, I know on the ICE table, y is just concentration. They actually want you to find moles. So again, we're not quite done yet. This is actually the concentration. This is the amount of energy I put into the bulb after you divide the volume. How would I find just the moles of the energy that I tossed in? Well, we know C is equal to N over V. So N is equal to C times V. You take this concentration that we have, 3.25 for every liter that you have. Well, my bulb here, if I remember correctly here, we have a 5-liter container. I multiply it by 5 liters. How much moles did I actually pump in? 3.25 times 5 gives me 16.25. We're going to do our sig figs here. So I pumped in 16 moles worth of ammonia. So let's backtrack. My container was 5 liters. By pumping in 16 moles, you divide by 5. The concentration ends up being 3.25. 3.25 was what I began with. I started off with no reactants. they gained in this amounts here, and overall using that as your y value, we can hit this equilibrium constant. At the end of the day, we still have our products being favored. So y is roughly 2.25. Even after we minus 1, that's only 2.25. We still roughly have way more products than reactants, which is what it means by Keq is bigger than 1. Right? So again, just ice table, it just takes a little bit of practice of setting up the problem. What I wanted to show you in these questions here is for these sides here, it was easy to predict which sides are plus, which sides are minus, because I assumed I didn't actually punch any N2 or any H2 in. I can't drop any lower than 0. That automatically predicts for you which side is plus. If one side is plus, the other side is minus. All we're going to end off with today, we're going to practice some more ice table style questions is, what if this problem were worded, yeah, I know I pumped in NH3, but I'm going to pump in some N2 and pump in H2. So if I have different amounts of N2, H2, I'm going to randomly have different amounts here. So the chance of me being at equilibrium right away is very low. However, because I have all three amounts, I'm not necessarily sure. Based on the Keq, this time it does say products are favored. Based on the amounts that I pump in, I don't know which side's going to be plus, which side's going to be minus. So in that situation here, I'm going to do one last little twist. And this twist here, what we're going to do in that setup here is we're going to try to find what's referred to as the trial Keq. So let me just introduce this to you here. We'll call this a trial Keq or a test Keq. For short, we'll just call this Q. Right? And essentially, trial Keq here, it helps decide whether the reaction, our accent is reaction, reaction proceeds forwards, so as reactants become products, or backwards to reach equilibrium. You could refer to that as a shift. You can say, oh, it shifts towards the right or shifts towards the left, but usually we reserve that terminology shifting when we're poking at the equilibrium. I do this, and then equilibrium wants to respond. So in this case here, I'm just using the terminology. Which direction does it proceed? Which direction does it head to hit equilibrium? Basically, which side is plus on an ice table style question. And it's actually really easy here. In this case here, for trial Keq, which is Q, it's basically Keq. It also is this sort of product over reactant ratio, where in Keq we had to guarantee we had the equilibrium constants here. Q is actually the Keq, which is like this product over reactant ratio, but at your initial concentrations. Right? So it's like sort of taking, these are the random amounts that I tossed in, use these amounts, test what the value currently is, and then we'll compare it. What should it be when it reaches equilibrium? If I'm too low, it's going to shift one way. If I'm too high, it's going to shift the other way. Right? So the Q here, which is basically Keq at the initial concentrations, it is also product over reactant. It's this ratio at initial. So let's just walk through a quick problem or two here. So I'm going to give you an equation here. We have the expression CO and H2O. I think I borrowed this from your textbook again. This becomes H2. Initially, 1 molar CO, H2O, CO2, and H2 are placed into a vessel. I've already given you the concentration, so I helped you with that part. You don't need to divide by volume this time. Given, I'm going to choose a Keq value here of 0.50. They could ask you part A, B, C. Part A is which way does the reaction proceed to reach equilibrium? So which side is positive, which side is negative? And then B, I want you to find the equilibrium concentration, similar to the questions we were doing. Find the equilibrium concentration. I could have chosen any chemical. I'm going to choose of CO. Okay, just to make sure you have the ice table, that's how it's set up. Let's try it out here. There is a sense of time passing because we're given some initial amounts, and later on we're told it's at equilibrium. So that's my hint. It's going to need to be ice table. So let's try it out here. We'll use the balance equation as our heading. CO and H2O is in equilibrium with CO2 and H2. I have my ICE down the side. This time, just to keep the numbers simple here, I just use 1 molar for everything. So initially, I had a container. I pumped in 1 molar of everything. So 1 molar CO, 1 molar H2O, 1 molar CO2, and 1 molar H2. Those don't have to be the same. If I want to pump in more water, pump in more CO2, I can. We'll do that in the last question. But in this case here, just to keep things simple, they're all 1s. I know I'm probably not in equilibrium because I just randomly toss these amounts here. I know by the time we reach equilibrium, the constant is supposed to be 0.5. Because this constant here is less than 1, it should tell me reactants are favored. So already I'm sort of leaning towards, well, if I have all even amounts here, well, by the time I reach equilibrium, I should have more reactants than products. I'm already sort of assuming this side on the left side should be plus, the other side should be minus. But sometimes, especially when there's actually coefficients here, sometimes it's not so easy to predict. What I want you to do in this question, it's not so clear which side is plus or minus because none of the sides are 0. Because if we can't drop any lower than 0, we have to have that side being plus. This side, we actually have all 4 amounts, but I still may not be at equilibrium. What I'm going to do is I'm going to take these initial amounts here, and I'm going to imagine testing. What is my equilibrium constant using these numbers? So let's do the equilibrium expression, products over reactants, CO2 and H2 all over CO and H2O. I'm essentially doing KEQ, products over reactants, but unlike using the equilibrium row as I should, I'm just using all the initial amounts. And in this case here, I kept the numbers really simple here. Basically, everything was a 1. It's like 1 times 1 divided by 1 times 1. Well, my test value is currently 1, right? Basically, I'm just trying out my KEQ. Based on the amounts that I have right now, it's like my ratio is 1. What should it be at equilibrium? At equilibrium, it should be 0.5. So at this point here, a couple things could happen. It's possible when you actually just punch in these random amounts, it is possible, although rare. The Q is exactly what it should be, the KEQ. That means the system is at equilibrium. You just pumped in the exact right amounts that you don't have to shift anymore. It's basically going to be at equilibrium. In my situation right now, my Q value is 1, my KEQ is only 0.5. My Q value happens to be too big for KEQ. So my Q value happens to be 1. I'm supposed to be 0.5 when we're at equilibrium. So what actually has to happen is the KEQ is sort of a constant at our temperature. I'm not changing the temperature on you. Basically, you can think of this here as my Q value, using my current product over reactant numbers, my Q value is too big. My Q value actually needs to get smaller. It's going to approach KEQ by getting smaller to become 0.5. Well, if you remember here, this Q is actually products over reactants. How would I get this product over reactant ratio to become a smaller number? Well, if I want a fraction to overall to become smaller, I need the numerator to shrink, I need to lose products, I need the denominator to increase. So in this case here, we can say the system, I'm going to use the terminology of shifting, or approaches shifts left. And how do I know it's left? Is because if I go to the left, I'm going to end up forcing more of the products to become reactants. I'm going to lose products. Losing products means this side is a minus, what I had sort of assumed in the beginning, and I would actually gain reactants. So we went through all that work just to decide which side is plus, which side is negative. Just for completeness sake, before I finish that problem, it is totally possible that your Q value, when I tested out my trial value, I compare it against the 0.5 it should be, maybe my trial value, my amounts aren't big enough. So in that case there, the Q would actually want to climb. For that case here, if the Q wants to climb, for my fraction to get more and more large, I need my product to increase, my reactants to decrease. In this case here, the system, you can say shifts right, or you can say it proceeds right. And in that case there, if it proceeds right, I need to gain more products, so I need to pick up more CO2 and H2. I need the value to be bigger because perhaps my KEQ is actually a larger number. So this test value helps you decide which side is plus or minus when it's not very obvious. I'm just giving you a sort of sample practice here because I'm not knowing any of the numbers on the equilibrium row. This is the time that I actually use X. The nice thing again about the change sign is it has to follow the mole ratio. Everything is a 1-to-1 ratio, so we're just going to go plus X, minus X, minus X. If you have the I and the C row, you just do the math. What's 1 plus X? Well, 1 plus X. 1 plus X. What's 1 minus X? 1 minus X. 1 minus X. Even though I don't know what X is, I'm going to still use that as a placeholder. Whenever you have the numbers or the placeholders for the equilibrium row, you're ready to now punch it into the true KEQ. The KEQ, we had already done the expression earlier. Earlier, it was the CO2 and the H2. All that is identical, but because KEQ here has to use the equilibrium values, we have to use the placeholders on this E row here. Again, this is a standard Chem 12 problem where they've set it up very nicely that you don't need to use a quadratic formula. We're thinking in this chapter, I can probably use a square root. So the Keq is supposed to be 0.5. Upon doing this shift towards the left here, the ones have actually changed a little bit by x. I want to figure out what the x is going to be. Keq is supposed to be 0.5. The products are going to be 1 minus x, so 1 minus x, 1 minus x, divided by 1 plus x, 1 plus x. I'm going to do a problem with you later on that does involve a quadratic. In this case here, because these two things are just being squared, I'm thinking of this here, 0.50. The top is like 1 minus x squared. On the bottom is 1 plus x squared. Because both of them are being squared, even though 0.5 is not a nice number, you can still take a square root of 0.5, no problem. Let's take square root. So take the root of both sides. I'm getting roughly 0.707, and the square root actually kills both the squares. We get 1 minus x and we get 1 plus x. We're going through all this work here to solve for x. Let's bring the x here up. So 0.707, it has to distribute into the 1 plus x. I'm going to just factor that in there. 0.707 plus 0.707x has to equal to 1 minus x. I'm going to collect on my like terms, so move all the x terms to one side here. I'm going to move the minus x over by adding x, so 1.707x. I'm going to move the 0.707 over by minusing it. 1 minus this answer here, this gives you 0.293. And therefore, x is equal to 0.293 divided 1.707, and this gives you here 0.17. Right? Again, this one here, I'd say it'd probably be a 4-marker or 5-mark question. You would have gotten 4 out of 5 right now. What's missing? Even though it was a lot of algebra, right, you solved your way, yes, I got this x here. Always do yourself a favor and go back and reread the question. We had already answered the problem, which way does it proceed? It proceeds, in this case here, to the left, because I need to gain reactants. But they were asking for the equilibrium amount of CO. Let's look on our ice table again. The equilibrium amount of CO was actually the placeholder 1 plus x. They don't want you to just give me x. They want you to actually go, the CO at equilibrium is actually 1 plus this x, and therefore your answer is 1.17. So go back and always reread the question. Even though it was a lot of algebra to actually get to x, I'm going to show you in the next question it's even harder to get to x, but do yourself a favor, reread the question, figure out what they were actually after. Right? So we use this child Keq value. We basically use the current initial amounts here. We compare it against Keq to decide, do we end up plussing on the left side or plussing on the right side for it to get closer and closer. Basically, how does Q need to change so that it ends up becoming Keq? The Keq is a constant for that temperature. That becomes your sort of test value, and then Q needs to get closer and closer to that Keq. Just for fun, I'm going to give you a very similar problem here. I'm going to even use the same equation here. I'm just going to show you what it would look like if you need a quadratic. Just use this as a nice challenge problem. You won't just see anything as difficult as this, but see if you can follow along with my logic here. So just for fun here, we have CO and H2O in equilibrium with CO2 and H2. I'm going to give you our Keq here is currently 10, right? So different from earlier, I'm at a different temperature here. You can already do some interpretations. If K is bigger than 1, that means I should have more products. Right? Products are favored. Right? Again, I'm going to just sort of hint out, I'm going to have an initial, a change, equilibrium. Unlike using similar numbers where you could just do a square root, I'm going to give you just 4 random numbers. So let's say I'm going to pump in 1 molar CO, 2 molar H2O, 3 molar CO2, and 4 molar H2. Right? So those are the amounts here. Again, these ones here are all concentrations. The concentrations here do not have to follow the mole ratio. This just is up to you how much you decide to pump into your bulb. All of them are concentrations just for simplicity. Again, because none of the sides are actually 0, it's not so clear which side is plus, which side is minus. So what we need to do, in that situation, we're going to use our Q value, use this test value. Let's figure out the expression for Q. Q is products over reactants, so same as earlier. I'm using the same equation so you have a little bit more familiarity. And what I'm going to do is I'm going to use the initial values. Based on the values I put in, what is my Q value? My Q value currently does say products are favored because we have a lot more products, but still what I don't know is, do I have enough products? Do I have as little reactants as I need for this ratio to actually be 10? I'm actually doing this to test it. So here we go, 3 times 4 divided by 1 times 2. It's essentially Keq, but I'm using the initial values. 12 divided by 2 here is 6, right? So that equilibrium constant here also specifies my products are favored. However, again, I see that my Q is not equal to Keq. Well, I just randomly toss in these amounts. It would be a magic if I actually hit equilibrium amounts. But what I have to do here is my Q this time is too small for Keq. Earlier it was too big. Because my Q is currently too small, my product over reactant ratio has to go bigger. And if this ratio here wants to go bigger, I need to gain products and I need to lose reactants. So which side is plus and which side is minus? You can either memorize it, but I think it's easy enough just to see it from here. Well, if I need to gain product, my system actually needs to proceed towards product, or it needs to proceed right. So even though I already have a situation where I actually have more products, still, this side is not big enough here. My ratio is only 6. I need even more products for my ratio to actually end up as a 10. So I've decided which side is plus. This side here, which is minus, I already had very little to begin with, but you can't just say, oh, this is little, this is plus, because it depends on what the Keq should be at that temperature. Just like the earlier question here, we don't happen to know what the change is, so let's go through use x. So far, these are all in a 1-to-1 ratio, so it's just all x. If you have the I in the C row, you just do the math. 1 minus x is 1 minus x, 2 minus x, 3 plus x, 4 plus x. Your regular Chem 12 would just stop there. It would say, okay, it proceeded right, great, it needs to climb. Just to give you a challenging bonus here, let's try to figure out, because the numbers aren't so nice, we will actually use a quadratic formula. It is going to take a little bit more work for get to x. And let's say we were trying to do the same as earlier. Maybe I wanted to find the equilibrium amount of CO. So here's how this works here. We're going to write down our Keq expression. Our Keq, even though I'm ready to put in my numbers, I still always write it out with the chemicals, just in case there's powers I don't want to accidentally have dropped them. So the Keq value here, by the time we're at equilibrium, the Keq should actually hit 10. The question here is, what x would I need so that by the time these have changed to equilibrium, we actually have a ratio of 10. This time they didn't choose really nice numbers, so we can't do a square root. This time we are actually stuck doing the math. So in this case here we have binomials. 3 times 4 is equal to 12. 3 times x is 3x plus the 4x here. So that's going to give you 7x. X times x gives you x squared. That's just the top. Same thing, I'm going to FOIL on the bottom here. 1 times 2 is 2. 1 minus x. Minus x times 2 is minus 2x, so that's minus 3x overall. Minus x times minus x here gives you plus x squared. Right? So you see that the problem becomes mathematically more challenging because we're not allowed to use a square root. Similar math though, I need to bring up this term here onto the left side. 2 minus 3x plus x squared. This has to equal to the right hand side. Again, you're not going to get anything mathematically as hard as this, but we still have one equation, one unknown. You can technically solve it. Let's distribute the 10 inside. So this becomes 20 minus 30x added to 10 x squared. This is matched up to 12 plus 7x plus x squared. Usually when you do algebra like this, you kick everything that doesn't have x over the other side. But in this case here, it looks a lot like a quadratic because I have some squared terms, I have some terms that are power 1, I have some constant terms. So what I'm going to do here is I'm going to move everything over to one side. Doesn't matter which. So I have an x squared here, let's minus an x squared. Let's kick everything over to the left side. So I'm going to have a 9x squared. I already had a minus 30x. I'm going to minus another 7x over. So minus 37x. I had a 20. I'm going to minus off 12. And this one here gives me a plus 8. Right? So that's my quadratic here. If you remember from your math classes, your quadratic was this really scary looking thing. Negative b plus or minus the root of b squared minus 4ac divided by 2a. And essentially, I would need the a, in this case here, is 9. The b is actually negative 37. And the c is actually 8. So, mathematically more challenging. Let's see what we get. We want to do a minus of a negative 37 plus minus the negative 37 all squared minus 4 times 9 times 8. 4 times 8 times c. All over 2 times 8. Let's clean this up a little bit here. Negative and negative just becomes positive. Let's plus minus. Usually what I like doing is I just like typing in just what's underneath the hat here. Negative 37 squared minus 4 times 9 times 8. Try it for yourself. Make sure you're able to get 1081 underneath the square root. And I just go square root of that 1081. Mathematically, I have two possible solutions. 32.9 divided by 2 times 9, which is 18. At this point, I'm ready to separate my plus and negative root. This doesn't mean one of my answers has to actually be positive or negative. It just means at this step in the math, one of the answers takes 37 plus, 32.9 over 18, and the other takes 37 minus 32.9 over 18, depending on the actual values. Like this problem here, we're actually going to see both of them are positive, so be it. 37 add this 32.9 divided by 18. This gives you your answer could be 3.9, or 37 minus 32.9 divided by 18. Make sure you do the top part first. I'm getting 0.23. Right? So just to again imply to you what axis would actually solve this problem, the axis could be 3.9, could be 0.23. Now, how is this possible? I thought we were going to end up reaching just one equilibrium. Why am I getting two answers? Sometimes this x here turns out as negative, right? And if we're talking concentrations, well, concentrations can't go negative, right? That's somehow you can actually reject it. In this case here, we're actually going to look at this number. 1 is 3.9, 1 is 0.23. I notice, again, x here is the change, how much the CO has to drop by. If x were actually 3.9, the 1 can't drop by 3.9. I can't drop into the negatives. So based on that there, I know I have to reject this 3.9. Although it's a mathematical solution, this is not a physical solution. So my answer here, even though it took way more work, it just gets to the 0.23. Again, you're not going to need to do quadratic, that sort of math here. We were able to find x, but still, go back, reread the question. Let's say we matched up to the earlier question. Maybe I want to know the equilibrium amount of CO. It could have been anything. Well, this time, even though it was way more work to actually get to the x here, it's just going to be 1 minus x. Well, 1 minus this 0.23, and therefore we've gotten our answer. By the time we're at equilibrium, we've still lost. Even though the CO and the H2O on the left-hand side was already really small, we still had to lose a little bit more, gain a few more products, so that my Q, currently it's a 6, can climb to it being 10. The 10 here never changes. This is what it should be at that temperature at equilibrium. The Keq here utilizes the equilibrium constants. Q is basically, let's just try out my values right now. Does it need to get bigger, like in this situation, shift to products? Does it need to get smaller, like the earlier question, shift to reactants? Right? You only need to do this when it's unclear which side is plus or minus. Usually they help you out. They put one of the sides as 0, so you automatically know which side has to gain. Right? So keep practicing your way through. That does finish off this chapter here. We'll do a quick summary in tomorrow's lesson, and that'll be it. All right. If you have any problems, let me know. Thanks, guys.